Okay, line integrals. So we have these goals to be able to compute just the scalar line integral along a curve. The scalar line integral is kind of an abstract idea and just presents this notion or this process of integrating along a curve. Um, we're going to find that we don't do scalar line integrals sort of in that we don't think of them as scalar line integrals. We're more interested in these kind of vector line integrals where we're computing the work done as we move through a force field, or we're computing the flux or circulation of a vector field. Another thing to note right off the bat here is the notation in this section is quite varied, and you're going to have to just be wary of that. And there's a lot of different ways of notating the exact same thing, and it seems really weird and frustrating. Pay attention to that and just kind of develop sort of the visual cues so that you know what each of these weird collections of symbols is representing. As we've been promising all along, we finally begin to talk about the idea of flow across a boundary in 2 dimensions. Um, we begin by defining the line integral in its own right. That's what the scalar line integral is referring to. And this is an idea that comes up in complex analysis if you're interested in hearing more about it. And I will actually teach complex analysis in the spring of 2022. The line integral, once we set up the theoretical sort of definition of the line integral, then we're going to use it to compute flux and circulation. And then here's my comment again about symbols. The line integral is symbolic, and you actually have to do something to it in order to begin to calculate. Unlike sort of the regular integral, where we have the integral from a to b f of x dx, all you have to do there is find the antiderivative, plug in b, plug in a, and subtract. Here you actually kind of, you're given this symbolic integral, and you actually have to convert it into an integral that you can actually do. Let's do a quick flyover of the section. So we begin by introducing scalar line integrals, and it's a pretty intuitive idea. You've got this curve in space. You chop it up into little pieces of arc length, ds, and then you throw in an integrand if you want. So what this represents very abstractly is this function evaluated at points in space, x, y, and z, times a little segment of arc length, ds, and then you sum it up over the curve. This is the symbolic representation of it. To actually calculate one of these integrals, you have to parameterize the curve, and you then have to substitute that parameterization into the definition of the integral. We'll do a lot of that in the examples. So to find the value of a line integral, let's look at this really simple example. So we have just a constant function of 2 variables, and we're interested in integrating this along C, the upper half of the unit circle. So what you have to do is parameterize the upper half of the unit circle. And actually this example isn't doing that, but you would parameterize the upper half of the unit circle and substitute it into the integral and evaluate it. In this case, it's not as complicated because this function is constant. We can factor it out, and what we're left is twice times the arc length of the curve that we're integrating along, right? If you just integrate one ds, then what you're really computing is the arc length of c. Because the constant 2 can come out, you compute the arc length of c, that's pi, you multiply by 2, you get 2 pi, and you're done. All right, let's carry on. Now, if you have a more complicated function than a constant function, you have to parameterize the curve that you're integrating along. So you build a parameterization from all of the knowledge that you've developed over the course of the semester, and you express that as a function, as a vector valued function. When you compute this, you compute the derivative, you take the magnitude of the derivative, which gives you arc length, and then you multiply by the integrand f evaluated along the curve. Then you've got an integral over the parameter range a to b that looks like this. So symbolically, you might be presented with a line integral that looks like this, but you have to do the work of parametrizing c using a vector valued function r. You have to find the derivative of that vector valued function, compute its magnitude. You look at the values of f along the curve, you look at the magnitude of the derivative of the parameterization, and you integrate over the parameter range a to b, and that gives you the scalar line integral. Now it's good practice to do a few of these just to get it out of the way, but there are very few applications that use this scalar line integral just on its own. What we're really interested in is vector line integrals, and even more interested in computing work, flux, and circulation. All right, so what we might be interested in as we move along a curve is perhaps the interaction between the direction of the curve as you move and the vector field that you're floating in. And in fact, this quantity is called work. And if you take the force field and you dot it with the tangent vector along the curve and you integrate it, you get the work done by moving through that field along that path. We're going to revisit this several times in the coming sections. For now, I'm just interested in being able to calculate it. So how are we going to calculate this? Remember that the force is just, a vector field. T is r prime over the magnitude of r prime. And remember that ds is secretly the magnitude of r prime dt. So a lovely thing happens here. The magnitude of r prime in the denominator of t cancels with the magnitude of r prime that occurs naturally with this little ds, and you get a really simple expression. To compute the line integral f dot t ds, you evaluate the vector field along the path r of t, and you simply dot it with r prime of t, integrate it over the parameter range, and you're done. This will give you the work, the physical quantity work of moving along this trajectory through this field. Let's keep going here. There's a few examples that I'll let you work through. There are several different notations for this kind of work integral. There's, let's see here. There's f dot t ds, okay? That turns into this guy, which often is expressed as f dot dr, strangely enough. So that's one. If you keep going, there's f dot dr. There's also some textbooks use dx, dy, dz. So f dot dr is the dot product of f with dr, which people often express dx, dy, dz. So you will often see if f is a vector field of the form pqr, then f dot dr is the same as integrating p dx plus q dy plus r dz. What I usually do is immediately shift back to f dot dr notation, and then I ignore this. But it's helpful to understand what's going on here. All right. Vector line integrals have lots of fun properties. They're linear, scalars can come out, and the sign changes if you change the orientation of the curve. Also, a very powerful feature of vector line integrals is that if we have a curve that's made up of a collection of segments, we can break up the integral along each of those segments, do the integrals independently along each segment, and then add them back together. This is pretty reminiscent of integrating back in Calc 2, where you could break up the interval of integration at any point in the middle of the interval, say a to c, c to b, and then add them together. It's a generalization of that idea along curves. Okay, Continuing, applications of line integrals. There's density applications. This is using just the scalar line integral to compute density along, say, a wire of varying density. There's computing work, which is just f dot dr integrated along the curve. And then there's flux and circulation. Flux is actually just the same as work in this case. It's f dot dr. And circulation, I'm sorry. Circulation is the same as work. It's just integrating f along ds. But it's often referred to only in the context of closed paths, where C is has the same starting and ending point. So that's circulation. It's essentially work along a closed path. And then flux. Again, we're mostly interested in flux along closed paths, although it doesn't have to be closed. Flux is integrating f dot n ds around the curve. So in this case, you have to compute the normal vector around the curve and then integrate the line integral. And you also have to be careful about the choice of normal vector. Usually it'll be specified in the statement of the problem, but remember, for any curve, this is a normal vector, this is a normal vector. For any curve in the plane, there are two possible choices for normal vector, and you have to make sure that you're choosing the appropriate one. If you're off, like if you choose this one and you were supposed to choose this one, it'll introduce a minus sign. Okay, we're going to do lots of examples of this, calculating flux across a curve, calculating the circulation across a curve, and let's do this just by example. So I'm going to jump over to the notes now and begin working some of these examples. In exercise 48, we're just computing a scalar line integral with no eye towards application to start out with. Okay, remember how this works. C is the line segment from -2, 1, -1 to 1, 2. I usually start by plotting. All right, so we want to start with a sketch, and we'll just plot these 2 points and plot the path that connects the two. All right, so we're talking -2, -1, up to 1, 2. Looks like that. All right, remember that this is just symbolic. We can't evaluate this as it is. We've got to come up with a parameterization of the curve. So let's do that. There's a lot of different ways that we can go about this, but I think the easiest thing is to use the PQ method and generate the equation of the line from way back in chapter 2. So we know that, say, PQ, the vector from P to Q, is given by Q minus P. So that's going to be 3, and so that's 1 minus -2 and 2 minus -1, 3. And we don't really care. Well, I guess we'll keep it. It doesn't matter. And then the line, R of t, is the starting point, -2, -1, plus t times 3, 3, like that. All right, just to double check, what's the parameter range here? When t is equal to 0, we're at P, and when t is equal to 1, we're at Q. So this does what we want in the orientation that we want. Next, we have to figure out r prime of t, and that's just 3, 3. And then we have to figure out the magnitude of r prime of t. And that is going to be, let's see, 3 squared plus 3 squared, 18, square root of 18, which is just 3 root 2. All right, so the pieces are starting to fall in place. Let me give myself a little more space. All right, so the parameter range, the limits of integration are 0 to 1. We have to replace x with what it equals along the parameterized curve. So in this case, we have the constant 4 times x is going to be -2 plus 3t, and all of that's cubed, and then finally 3 root 2 dt. And then we just jump over to our favorite program and evaluate the result. Let me jump over to Sage and do that real quick. I'll pause and come back. Okay, jumping over to Sage, that comes back as -15 the square root of 2, whatever that means. All right, let's carry on. Let's find the work done by this force moving along this curve. All right, that's one of these integrals. So W equals the integral along CF dot dr, where r is the parameterization. What do we need to do to figure all this out? We first need r prime. So let's compute r prime. That's going to be minus sine of t, cosine of t, and 0. We also need f along r, which I'll denote as f of r. And what that is twice times the y-coordinate, so 2 sine t, 3 times the x-coordinate, 3 cosine t, and then finally x plus y, so cosine of t plus sine of t. All right, what do we do next? We want f dot dr, f of r dot r prime. So we get -2 sine squared t plus 3 cosine squared t, and that last term goes away because of the 0 in the r prime. All right, we're ready to build the integral. This integral is actually the integral from 0 to 2 pi of f of r dot r prime, -2 sine squared t plus 3 cosine squared t dt, like that. And let me just double check my notes here. All right, and we're ready to integrate, I guess. Once again, jumping over to Sage, we get pi. All right, let's look at the next one. Now we've got a line segment in 3 dimensions. Give myself a little bit of space to work. But it's just another one of these scalar line integrals, so no application going on here. I'm not going to even bother to plot this. I'm just going to label this P and label this Q and build the parameterization of the line. So we need the vector from P to Q, which is going to be 2, 2, 3, minus 0, 1, 1, like that. That yields 2, 1, and 2. The line, or the parameterization that we need, r of t, is going to be the starting point, p, plus t times pq, which is 2, 1, 2. All right, if we're going to do ds, we need the magnitude of r prime, so let's compute r prime first. That's just 2, 1, 2. And the magnitude of r prime is just the square root of the sum of the squares, which is 3, it looks like. That's pleasant. All right, so we've got the magnitude, we've got the parameterization. It's now time to rewrite this integral. The parameter range is just 0 less than or equal to t less than or equal to 1, so that's our limit of our limits of integration. What's y along this parameterization? It's the middle coordinate of r, so it's 1 plus t. The magnitude of r prime is just 3, and dt, and then you can jump over, you can do this one by hand, or you can jump over to Sage, and you'll end up with 27 halves. All right, let's do 61. So in 61, we're evaluating another line integral over this slightly different notation, and I'll show you how I handle this notation. We're going over the path, we're given the parameter range, which is pleasant. I usually just translate everything in sight into notation that I'm comfortable with, which means I'm going to rewrite r of t as 2t, 10t. Great, and I know that this is secretly cf.dr, where f is the vector valued function, or the vector field x, y, because that's on the dx term, comma y, because that's on the dy term. And this is secretly a dot product with dr. So if this is the result of a dot product of f and dr, then we know that the x-coordinate of f is xy and the y-coordinate of f is y. So now we have all the pieces to just carry on. Let's compute r prime. That's 2 and 10. And let's rewrite this integral. What's the parameter range? It's 0 to 1. That's over here. We need to express f along the path. So x is equal to 2t. Let's just do that over here. Let's do f of r right here. So that's x times y, so that's 2t times 10t, 20t squared, comma y, which is just 10t. And we need to dot that with r prime, so we're going to take 20t squared times 2, 40t squared, and 10t times 10, 100t dt. And now we just compute that integral, and I'll check my notes here. No, I don't see it in my notes here. Let me just jump over to Sage and compute it so that I don't make a computation. All right, that works out to 190 thirds. 190 thirds. So just to recap here, it's a good idea when you're faced with these kinds of symbols to just go back to something you're comfortable. So translate it to symbols that you're comfortable with and then work in that context. That's what I usually do. All right, 70. So now we're asked explicitly to compute f.dr, where f is given by this expression, and c is the segment along the unit circle going counterclockwise. So let's sketch that. So that's this curve in this direction. We need to parameterize that curve, so we'll write it r of t. And this is just the unit circle, so it's cosine of t, sine of t. And the parameter range that traces out this quarter circle is t between 0 and pi over 2, and it's oriented correctly. All right, if we're going to do f.dr, then we need r prime, which is minus sine of t cosine of t. And we need f of r, so that's f evaluated along r. And that looks like this, 1 over cosine t plus sine t, 1 over cosine t sine t. It's just repeated. Now we need the dot product, so we're going to compute f of r dot r prime. And that gives us a scalar minus sine plus cosine, oops, dropped my t, minus sine of t plus cosine of t over cosine of t plus sine of t, like that. All right, we're now ready to build the integral. This integral is the integral from 0 to pi over 2 of cosine of t minus sine of t over cosine of t plus sine of t dt. Now, this integral, you can't do this one by hand, or you might be able to, but it would take a lot of work. So you can try it in Sage, but even Sage is going to choke on this. It's just too symbolically complicated. So what I do in this situation, if I want a value, I'll jump over to Sage and do a numerical integral. Let me see if I can fire up Sage here and show you what I mean. So let me just quickly create a new worksheet. This is exercises. Oh, I think I have one of these. Exercises 6 point. Well, I thought I did. Exercises 6.1. Let's do exercises 6.2. Whoops. I'm giving up. Okay, let's use exercises 6.1 since we're not really doing anything deep here. Okay, this is exercise 6.2.70, and we'll do a numerical integral. See if I remember the syntax here. Cosine of t minus sine of t divided by cosine of t plus sine of t. And we want to go from 0 to pi over 2. And I think it's like max points. Nope. All right, let me pause while I go look that up. All right, so it looks like I'm missing an S right here. So let's try that again. And there we go. So what this gives you is the value of the integral, which is darn close to 0, and the error in that approximation, which is also darn near 0. This is 4 times 10 to the minus 17, which is as close to 0 as I ever want to be. So we can probably safely assert that this integral is 0. All right, moving on. Again, the setting up of these things is really the important aspect, not so much the evaluating. We've got computers for that. All right, let's find this line integral where C is the ellipse given by this. This is just another scalar line integral with no real physical interpretation, but it's good practice. So if we're going to do this, we're going to need the magnitude of r prime, which means we're going to need r prime. Again, I usually just switch over to notation that I'm comfortable with. So this is 2 cosine t, 3 sine t, like that. And r prime is then negative 2 sine t, 3 cosine t, like that. The magnitude of r prime is the square root of 4 sine squared t plus 9 cosine squared t. And you'd love to be able to simplify that, but you can't. You're stuck with it. Okay, so that's r prime, magnitude of r prime. The parameter range here is 0 to pi, and the function 1 plus x squared y has to be converted to go along the curve. So we have 1 plus x squared is going to be 4 cosine squared t times y, so that's another 3 sine t, and then times the magnitude of r prime, which is 4 sine squared t plus 9 cosine squared t square root dt. And this is another one that's pretty, you're not going to be able to compute this exactly, but you can jump over to Sage and use the numerical integral formula. Let's go try that again. The numerical integral formula is here, and we have, let me type that in for you. Well, I'm not going to type it in for you. Type that thing in there. Max points equals 100 is usually fine. And having done so already in my notes, this is about 29. And the error is, again, tiny. It's like on the order of 10 to the minus 13. So for all intents and purposes, it's 29. Okay, let's do 88. Here we're asked to find the flux across the curve C. So that's dealing with the normal vector to the curve. What's the curve? The curve is just y equals 0 from where x ranges from 0 to 4. So let's look at a graph of that first of all. So we're talking about just this piece of a line segment. And we need to parameterize it. We need to do all of the things. But we're going to sort of intuitively look at this vector field. How is it oriented? This vector field is really just a bunch of arrows that are all parallel to the y-axis, right? I'm sorry, that are all parallel to the x-axis. It's 5i, right? Like this. So if I were to draw this vector field, I would just have a bunch of horizontal arrows. So if we're interested in the flux of this field across this line segment, we can just look at it. We know that it's going to be 0. But let's just see the mathematics. Let's see how the mathematics play out. So what are we going to do? Let's parameterize this curve just in the usual way. So r of t is going to equal t 0, and the parameter range is going to go from 0 to 4. All right, and remember what the flux integral looks like. It's the integral along the curve of f dot n ds, f dot n ds. So we're going to figure out all of the various pieces. What's n going to be? What's the unit normal vector along this curve? It looks like it's just j. So we don't really have to do much calculation here. N is just j. And what's f along the curve? Well, it's a constant, so it's just 5 along the curve. So what we end up with is the integral c of f dot, of 5 comma 0 dotted with 0 comma 1 ds. And this is nice because we don't have to do any work. This is 0, and so it doesn't matter about ds or anything else. The whole integral is 0, and we're done. So where does this geometric observation manifest? It manifests right here in this dot product. The vector field dotted with the normal to the curve is 0 along the whole path. Let's do one that's a little bit more complicated. Let's do the flux along this curve. Alrighty, the flux along this curve, let's parameterize it. Let's plot it first. So the curve is, of course, just a circle of radius 3, and it's oriented counterclockwise. This circle has radius 3, so we'll write r of t as 3 cosine t, 3 sine t, and the parameter range is 0 to 2 pi. So that's going to get us what we want. Remember what flux is. It's the integral around c f dot n ds. All right, if we're going to do all of this, we need a normal vector, a unit normal vector, and we need ds. The unit normal vector, once again, we can do this without calculating. If I'm at a point here, what is this point? It's 3 cosine t, 3 sine t. What's a vector that points normal to that and is a unit vector? It's just cosine t sine t without the 3. So luckily we can sort of reason out what n is. we'll just tuck that away. Let's compute ds, or in other words, let's compute r prime and then the magnitude of r prime. R prime is -3 sine t, 3 cosine t, and the magnitude of r prime we see is actually just 3. What's f along this curve? F along the curve is, actually, once again, let's do this up here separately. So f of r is the vector. X squared is going to be 9 cosine squared t plus y cubed. That's going to be 27 sine cubed t, comma 2xy, so that's 18 cosine t sine t. So there's f of r. And we need to dot that with the normal vector. So let's do that. Dotting that with the normal vector, boy, this is getting messy. We get 9 cosine squared t plus 27 sine cubed t times the quantity, or the quantity times cosine of t. That's this component of n, plus 18 cosine t sine t times sine of t. So we'll just get a sine squared there. All of that times the magnitude of r prime, which is 3, dt, and the limits of integration are 0 to 2 pi. This, again, is an integral that you could do. You could grind away at it with the half-angle identity and so on. If you work it out, interestingly enough, it all comes out to 0. But I'll leave that to you to figure out. So what we learned from this is that the flux of this thing across the curve x squared plus y squared equals 9 is 0. I'm going to go to the app that we've visited several times this semester, and let's kind of see how that looks, or get an idea of how, what that looks like in the context of this app. So here's a circle. Let's punch in the vector field from this exercise. So it's x squared plus y cubed, and 2xy. And let's update the field. And you know, it's not at all obvious, but the net flux across the circle is 0. So everything that's flowing in is balanced by all of this stuff that's flowing out. So the net flow across this red boundary, this circular boundary, is 0. That's how we interpret it. That's line integrals, work integrals, flux integrals, and circulation integrals. We didn't do a circulation integral, but it's essentially a work integral around a closed path. So once you feel like you've got this squared away, go ahead and hit the web work. Just a note here that exercises 52 and 84 are incorrect, and you should just ignore them as you work. Once you've got it mastered, just go ahead and hit the web work for Chapter 6, Section 2. Thanks.